you that weren't here on Friday, we went over this integration. And I went through it on the doc cam. So if you couldn't see the video with it on the doc cam, I looked at the video and it looks like the lighting, my camera just didn't understand it all that well. Normal stuff. I printed it all out for you. So you can follow this integration. So the problem we were doing, we're going to do another problem like this. And it's going to be even a little bit trickier, but we're going to follow the process so we understand what does a Bayesian do when they want to predict. They always do this sort of thing. This is what they're after. So this is the posterior prediction. Bayesians always do the same thing. Things that they don't know, they want to put a probability measure on. So they're upgrading that to a random variable. That's what makes a Bayesian a Bayesian. How do they operate? Through Bayes' theorem to get there in some way, shape, or form. So if you didn't know anything about probability, and you just wrote this down, you're thinking like a Bayesian. I want to know that. I want to condition on the data at hand. And I'm going to, for this problem, because all my x's, xi's are normally distributed, mean, mu, variance, sigma squared. I'm going to say you know sigma squared just to make the problem a little bit easier. But what a Bayesian would always do, or any probabilist in the world would say, I don't know what those things are. I'm going to condition on them, so they better be conditioned over here. And I know I've got some mu sitting around in this problem, and somehow I'm getting rid of it. So how do you get rid of something? There's only one way to do it. That's averaging it out. So marginalization. So what's its average behavior? However you want to think about that, it's margin. So that would just be true. I don't know what this thing is. I just know it's some distribution. It's just some notation. How do I get it? Since I now understand the setup of the problem that everything is IID, it's just this thing is how you get it. So I know what this distribution is. That's just from my sampling distribution. I condition on this stuff. If I were confused, I plug in the CapEx. I need to be conditioning on that everywhere. I conditioned on it here. I conditioned on it everywhere. But then I remind myself, if I know what the model parameters are, that's what IID-ness implies, is that the data doesn't have any influence on the future. But you can use the data to try to estimate the parameters. And that's the thing that ties everything together. So if you didn't know what the parameters are, you just use them. And this would be your forecasting distribution. But in reality, you don't get to know those things, so you need to average over them. So the Bayesian averages over their posterior distribution. So Bayesian is just always following just basic probability rules. So you get your posterior, and everything else is just probability theory. This is what it is in this case, and this requires a little bit of work, and that's what's on your piece of paper. So we're going to just walk through this. I want to just point out and ask the question, what if we didn't know sigma here? We would already have messed up in that thing. So that would mess you up because I ended up assuming that I knew what sigma was, and this is the sampling distribution for mu. So if you do go through the long-winded thing, the mistake would be here. You'd need this thing powered up right here. So if you didn't know what sigma was, all you're going to do in this problem is you're just going to integrate double integrals. So this will be the additional integral that you're going to put in here. It's just going to be likelihood of mu and phi given x. And then I'm just going to multiply by, let me write it out this way. I'm going to plug in this distribution again. X tilde given mu, and I'm going to say phi because I like to write it out this way. I'm going to start talking about the precision parameter. It's just 1 over sigma squared, so I can reparameterize this. No math, just transform. There's no Jacobian in there because the sampling distribution is on that. So if you change the x, you would need the Jacobian here. So, and then I need likelihood, mu, phi, x, and then I need my prior in here. And I'll just write down my prior. It's 1 over phi times 1. It's probably what you're going to use. And then you're going to integrate over mu and phi. So this is just what this would be. This is the same equation that we wrote down here. So it's still just this thing. You're just going to reparameterize it in terms of phi. So you're going to kick up a phi here. And this is going to be a phi 1/2 right in front of here. It's a direct transformation. So I'll just write that down. Phi 1/2 e to the minus phi over 2 x tilde minus mu squared. This thing, we know what this is. This is going to be phi to the n over 2, e to the minus phi sum of the xi's minus mu squared. There's a 2 in there. I oftentimes drop it under there, just because I start recognizing this as a gamma. So this is I goes from 1 to n. So the same likelihood we've always used, this is where everything's getting powered up, and we would have made a mistake right here. So, and then I've got this phi inverse right in here. Phi mu, d phi. This one is going to go from negative infinity to infinity. This goes from 0 to infinity. So you have 2 integrals to do. So you could just do this problem by scratch. Just write down likelihood times prior. You'd be good to go. So this will always work for you. And this will be x tilde given cap x. This will be proportional to it. And you're going to recognize this. What do you think it is? T. Very good. It's a t distribution. There's another way to do this problem. This is the way that I'm kind of leaning you through the problem on the homework, is I ask you to work out one more distribution. I ask you to work through this thing. That distribution. So how do I get this? This is just going to be likelihood phi mu if you want. I'm just going to keep that both places. So times 1 over phi times 1, if you will. This is just my prior pi phi times pi mu d mu minus infinity to infinity. So it's just likelihood times prior, marginalize out the stuff. So this is proportional to the joint posterior distribution. Pi mu and phi given x. So I ask you to work through this thing and give me that. So what do you have to do this problem? Complete the square. It's really this inner integral that you end up doing. So when I said to Hijal, I've got 5 ways to do this problem, I really have 4, and they're all the same. It's just changing the orders, what I'm starting with, and I can think about it different ways. But we could work through this problem right here. Then what I could do is do this. I can take my old problem, this problem that I've just worked out. I said sigma squared, but I'm going to just, it's conditional on, and if it's conditioned over here, just flip it upside down. You don't need any Jacobian on there. That's what our notation is helping us to remember. So I just take phi, so we can take our old answer that we worked out here and just reparameterize it, and I'll do that for you. I'll show you all you have to do. So I've got this thing. I can now multiply it by this. Get rid of that right here. So this is this problem that you just worked out. This is that problem that we just worked out. Now I can integrate this over phi. 0 to infinity. And this thing will also be equal to that. That would be equality right there if we left all the normalizing constants in here. So, and that would be a t. What distribution do you think this has?
Gamma.
Probably a gamma. It is a gamma. You have to complete the square to get the right gamma out of it. So it's not going to be s squared over n minus 1. Things are going to get a little bit messed around with there. But it's going to look like a gamma, and it will involve s squared. So it should look nice and tidy once you're done. And kind of make sense. And what I would do if I were you on the homework is think about this, think about its mean, and think whether or not that kind of makes sense. And it should make sense. So it's one of those answers where you go, yeah, that makes sense. So I'm not going to say means always make sense, but this is another one where things are pretty concentrated around the mean. It's got some skewness, but the mean of that gamma will make sense. So you could do the problem like this. You're really just doing this problem again, because you've already done the integral with respect to mu here. The common mistake I see is people use the prior right there. And you can't use the prior because phi is conditional on x, and you're conditioning on x here. So you need that conditioning in there, and that makes sense. If you didn't know phi right here and you did that, you would have made a mistake. Or if you didn't know x, that's what I meant to say. But you do know it.
So related to that mistake, like I'm wondering about the notation. So like we use pi for posterior and prior, and then for the thing right next to the integral, the sampling distribution, whatever you want to call it, sometimes we use f.
Oh, I'm sorry. Yeah. I'm just so used to making that arbitrary. This is your f to match the same one that we worked through over here. I called it pi because I get it that it's on x, so you want to make it f.
Right.
And that might be a polite thing. I remind myself I've done a Bayesian calculation, and that's a posterior with pi, so I recycle pi arbitrarily that way all the time. You can have your own arbitrary conventions. But yeah, that's the abuse of notation, is we're always using the same letters and recycling them in non-standard ways. If Chris wanted to use f pi there, I'd go, yeah, that's even better, but at some point you just write down the notation. So good thinking, this stuff used to bother me too. If you think you have a better notation, you're about to upset half the room. So lots of ways to do it. So work through that problem, maybe use this result, or if you want to verify and get some extra practice, do the two integrals again and recognize it's all the same math that you end up doing, no matter which orders you do it in. So Highjaw would say your 4 ways are really just one way. That's true. Okay, let's just glance at the integral we did. Remind ourselves how to do it, because I'm going to ask you in the future how to do this integral. I'll probably ask you for the work. We're going to also recycle this integral with high-dimensional normals and build some high-dimensional regression models out of this stuff. Everybody's doing high-D, so we can do it too, and we can see how to do it in a Bayesian format. So I don't want you to pluck your outliers if you think that's actual data. I want you to leave them in, and I'm going to show you how to transform all this stuff into some mean regressions, which is probably one of the best reasons to be a Bayesian. So if you don't like your regression model, you can just kind of change a hierarchy of your regression model and try to start pushing it in the right direction. So here's our integral from last time. Do you mind with the lights? Is that visible? Okay, so this is the integral just upstairs, is what we've done. All I did is expand the square. I chucked all my normalizing constant. If I didn't know sigma, this would be a mistake, but we can recycle this material for that unknown sigma problem if we condition correctly and work through pi phi given x. So get all the asymptotics right. So this is just expansion. This is just factorizing out some stuff. I probably could have chopped this out of the equation right here and said, since we're writing everything down to proportionality, and I left it in. So if you would have just swiped that out, that would have been fine, but it would have come back in some completion of the squared terms. So, oh, I guess I did cancel this term. I apologize, I was thinking of this term. I did get rid of it. So, anyway, if you get rid of it and it floats back into the equation, that's correct. Factorize that out, definitely don't lose that. So I worked through a calculation where I recognized which normal distribution this was. And so if I know which normal distribution it is, I recognize the expectation in the variance, I know what that integral is equal to. So I worked out which normal it was, I gave it a name, the expectation is E tilde, the variance is V tilde, and I work through those just by recognizing what's the quadratic term, flip it upside down, that's the variance. So you can never forget this because you can write it back in that nice compact form you learned in other classes and just expand the square and recognize where those terms are. So the expectation we get by taking the -2 linear term, that's this term, and multiplying it by the variance, what we just got. And that works essentially in high dimensions as well. We just have to understand what it means to invert a function, never divide by anything, multiply by inverses and do them in the correct orders. With scalars, none of that really matters. And then we just simplified a little bit, and that came out to be nice and tidy. This is essentially completion of the square right here, that if I know what the expectation and the variance is, I know what this integral is if it's written in this format. So I got quite a few questions about that. Let's just run over that just real quickly. So I got at least 5 questions about that, so I don't mind going through this step. Does anybody have a pen I can use real quickly? Got that G2.
Got my actual black pen.
Cool. 0.05. I think it'll be okay this time. All we did is this. So let's say I had an integral that looked like this. Integral 1 over 2 pi e to the -1/2 z minus, I'm just going to say e, since that's the letter I used before, divided by v. So dz, right here, this is square root 2 pi, and I'm going to tuck the v right under there. So that's a typical normal equation, minus infinity to infinity. What's that equal to? It's 1. You might be asking the question all of a sudden, how do I know that this is the right normalizer? How do I know everything? If I write this down, integral e to the -1/2 z minus e squared over v dz is equal to square root 2 pi v. I get that if you didn't have the v in there, you could do substitution and convince yourself that the v pops up in just the right place. But the 2 pi part might be a little bit hard. Does anybody know how to do this integral? Polar coordinates. Yeah, you can show this in polar. I'm not going to ask you to do that in this class, but if you're looking for it, you're looking for polar. So you take 2 of these, you multiply them into each other, and then you're set for polar. So you do a 2-dimensional example of it of 2 independent normals. You'd be ready to turn it into polar. When you combine the 2 things inside, you've got an equation that has to do with circles, so you'll recognize everything. And you'll do that RDRD thing, that thing. You'll know what R is in your equation, because that circle will pop up. If you've forgotten all that stuff, that's fine. So that's just how you do it. I get a lot of questions about how do you know things? And so I guess that's how we know it. Could I do it right now? I think I could. So, but it would look a little clumsy. So I probably need cold to help me with it. So we do know that. And so this tells us that integral e to the -1/2, I'll say z squared minus 2ze plus e squared. These are all over their v's. Right here, this is the term we're missing. So dz, this thing is still equal to root 2 pi v, but I can rewrite this, and I can rewrite this as e to the -1/2 z squared over v minus 2z e over v, and I can factorize this part out. And this is a -1/2 e squared over v. I have the plus sign here, but I have this minus sign over here, and I have to pull that out. So I can integrate this, dz, this is equal to root 2 pi v, and I can pull this thing out and just get rid of it here. It doesn't have a z, and that's why we can do this and write it here, plus 1/2 e squared over v. So every time I see this integral right here, I'm thinking that thing. And if I don't know the variance, if I know what the variance is, I can just forget about this part, but if I didn't know what the variance was, it'd be a mistake. Lose that part. So you're thinking to keep on that thing. That's what's right here. So this integral, once I have it in a form I recognize, I write out what my e and v's are. I really do this every single time. So I don't do the problem if I'm not in algorithm mode. mode. So sometimes I'm thinking, and I like that part, where I'm like, oh, I have to think about this, and that's what makes problems hard. Problems like this on tests, I go, oh sweet, I can just relax for 5 minutes, and my hand just takes over, and I start writing down, and I know how to double check myself because I've done it so many times. So that's where I want you guys to get. So it's not enough to have this piece of paper, it's enough to reproduce it. So I want you to reproduce it and practice it. So this is what we wrote down. Right here, we still have this part and we try not to forget about it. Easy to forget about, so that's why we circle things, put stars on things, all that. I rewrite everything, so I've just taken my E and my V and I've substituted in. Again, I always write this stuff out. I know where everything came from, so I can go back and double check everything. So if I just started cramming this stuff in and simplifying too soon and plugging it in, I would never be able to retrace my steps. So a lot of simplification, boom, boom, boom. 2 colors of pen is my trick for this. So I don't have 2 colors, but I would use 2 colors of pen if I were a student still going through all this. So I rewrite everything just in simplified form, and I'm just rewriting everything in terms of the quadratic term. So there's the quad, and I'm rewriting everything as the -2 linear term. So same exact process to recognize which normal it is, and we've done it 2 times in this problem. And then we just recognize everything. Same thing, we got some nice simplifications. So that's pretty nice. If you were running out of time on a test and you wrote it like that, that's fine for me. So if it's correct, I won't mark you off a point. So it probably doesn't behoove you to do this unless you're just out of time. And you're like, I want to make sure this is right. And I would probably do that on the test. Just come back through and go, I think I know what the answer is, so I better make sure it's right. And if it reduces to that, I'm going to feel really confident I've already graded my midterm turning it in. So I could say to myself, you don't even need to grade that. So if I ever been so smug to say that to somebody, once. Oops. Of course I make mistakes, so everybody does it. And you do the same thing right here at the status bar, and that's our answer. So let's just go back to the board real quick. And remember what to do over here. If you want to do that problem on homework 2, I guess we're calling it now, even though it's your 3rd exercise. You would just take this distribution, Ix tilde, given x, and sigma squared. We wrote it out like this. This is just a normal with mean x bar, and variance sigma squared 1 plus 1 over n. So if I wanted to rewrite this thing, here's what I do. So I call that 1 over phi. Bam. Couldn't be any simpler. Don't flip that stuff upside down. So it's just the parameter that just gets flipped upside down. So I've seen people flip the ends, but I didn't say to do that. I'm just touching that parameter and changing the way you think about it. So you just flip that thing upside down, and you don't flip all the other stuff. That would have messed you up right there. So again, when you're conditioning on something and you want to transform it, just do it. So likelihood you're not allowed to integrate over where did they come from? They came from sampling distributions, parameterizations, which were conditional on that parameter. So you're flipping over that conditioning. So no Jacobians yet. So you use that, you write down this normal here. Easy to do. It's a little weird to think about it that way when you're flipping it around, but once you write it out into expanded form and you're just looking for quadratic terms and -2 linears, it's just as arbitrary to you. So oftentimes, I will use sigma squared in the middle of the calculation. I'll roll it sigma squared until I'm ready to do something with it, and I'll flip it upside down. So I'll do it both ways, and I'm nimble. So just be careful. That's forecasting. We're going to redo all these problems. I want to redo everything with Poisson, tell you more just about probability theory, other things where you can kind of relax and it'll be, you're not seeing it for the first time. We'll do inference, we'll talk about conjugacy, we'll talk about the conjugate limit. We will see that we're really getting the Jeffreys prior. Soon I'll tell you exactly what that's all about, and we'll redrive all these priors that we've been kind of intuitively coming up with, and we'll see, oh, there's another direction we can come from. These priors fall out of it, and we'll do Poisson forecasting. Let me show you what I've seen people do. I used to walk around the department when I was just starting out, and I was one of the few Bayesians in the department, and I would ask, what do you do for this problem? And I would try to ask my classical counterparts, how do you solve this? What do you do? And I solved this on a committee one time. So somebody was doing this in their thesis, and this is exactly what they did. So xi's are Poissons. There's a parameter in there. If you know what this is, that's cool. These are count numbers. So this is 0, 1, 2, 3, 4. This is what I would call your fundamental counting model. You might call the binomial the fundamental counting model, and then express this from the limit of the binomial, but they're related to each other. And this thing is a number that lives between 0 and infinity. And let's say you want to predict. So you have a whole bunch of xi's. So you collect all this data right here, and then somebody asks you, what's the future look like? And I've seen this done. I'm not going to say that every classical or frequentist statistician would use this distribution. I believe that there's other forms for doing this, and I think people can come up with the right way of doing this. But there's no super smooth way to do it. How might you do it? You might say, oh, I'm going to say this. This is going to be Poisson, and I'm just going to plug in my best guess at lambda. What would your best guess at lambda be? X bar. Why? Let's see if I have to reduce your grade from inference class, because that's what the whole class is about. So it's the end of it. Give me some real reasons, though. So you gave me a process that derives it, but you gave me no guarantees. I'm going to have to go back and reduce that grade.
I don't know, calculated principle.
Okay. Anybody else? What's that?
Minimal sufficient.
Yeah, it's minimal sufficient, so that's true. Some more. There's other ways to use minimal sufficient statistics. That doesn't tell us how to use it.
Minimal variance.
Yeah, that's it. It's unbiased and minimal variance. Yeah, it meets that. So lots of good reasons to pick this. There's other estimators, but this one's hard to beat. That's nice because it's easy to compute. This is not right. I would consider this not great if n isn't huge. And you might be thinking, hey, we get data for free these days, but there are a lot of scientists and engineers who spend millions of dollars on data points. So some people are actually doing science and not just scraping the internet and seeing what kind of, that's weird. People talk about weird stuff. So not what I expected. They write papers on it. You can get big N for all kinds of reasons. But this has a problem with it. So we're not understanding the uncertainty inherent to that estimator. So the Bayesian's going to walk you through a calculation that's going to look like this. That's Poisson. That's posterior. So I want to walk you through this posterior and work through this posterior predictive distribution. Does anybody have a good guess as to what distribution this is? It's not a Poisson.
Yeah, negative binomial.
Okay. Love it. So negative binomials, if this is gamma, it uses the conjugate prior or the limit of, it'll be negative binomial. There's a little caveat, but awesome. Higher variance than the Poisson, so it's over dispersed. We're going to talk about all of that sometime after we get through a few little extra lectures. So we'll circle back, and then we'll get into Jeffreys and we'll get into computation. So that's what's coming. Let's switch the page for a second. We're going to recap all that. We're going to go through all that Poisson stuff super slow and make sure we understand through a few examples how Bayesians operate. Okay. Confidence. let's just come up with some definitions real quick. So confidence interval. I'm going to say set, but you can think of intervals. So I could have disconnected sets. So unions of sets. They all have the same properties, and we'll see an example with a set. You might be thinking of continuums, but I could take the same concept and break up those continuums. So confidence intervals, what are they? I remember being a Stat 101 student for far too long, and wow, they really hammered this one into me. What are they? So let's just give us some context. X looks like it's data. And let's say our goal is to learn theta, which are our parameters.
So like after you assume the distribution, you say that.
Yeah, so this is coming from f of x given theta. You could think of this as a vector or a matrix or something big. So this has all my i's and it's lots of data in there. We'll give ourselves a function.
And then you say like if I repeat this process, I'll contain the true parameter this percent of the time.
Yeah, I think you could say it that way. Anybody else want to clean it up so you don't lose those 2 points? I don't have a big problem with it. I think I know what you just said. Any stat students, McLeod, they must have done this to you. Please indulge us.
For the confidence set then?
Yeah, confidence interval that makes you feel more comfortable. LSG. No. David Roycroft. I'm going for stat majors.
And I was a similar thing to what Chris said, just that like it's the interval of values that should contain your true parameter.
Minus 100. That's the Bayesian interpretation. So you have to repeat it. So you have to repeat it so we don't know. So you're creating a probability measure if you just do it off of 1. So it's a process. So who else wants to go? We're not really losing any points. Okay, Michael, do it.
Okay, so the word confidence here means that now when you take your data, so we are not looking at the norm here, we take the data and then we simulate the estimates that we want, create a margin of error, and then we check if the parameter is within the confidence.
Yeah, so you're reciting how we did it on our homework. So you're reciting how to do it, and I agree, it is that. So basically what Michael just said is there's a parameter, we'll consider it something one-dimensional, but this could be in a high-dimensional space as well. So it's a way of creating a set of boundaries. So I might think of it like this. So if I get one set of data, I can compute these boundaries from that set of data. So I've got, let's just say I do this some number of times. I'm going to go j goes from 1 to cap j. I don't want to distinguish this with what n is in the analysis. That's already in x. But I do this over and over again. I construct an interval, and I see if it covers the true parameter. So, and I do it again, and I do it again, and I do it again with all of these different data realizations. In reality, if you had all those data realizations, you'd build a better interval and scrunch that interval down. So this is just kind of a mental process of what you do. So a confidence interval is a procedure. And if you want to say it and be real cheeky that, hey, everybody assumes something, it's a procedure that a priori has the property, and I want to write it down that way. So a process or procedure that a priori has the property of covering the truth. So the truth is the parameter, so I'll call it the true parameter. At some theoretical rate. So I.e. like 90%. And this might have a caveat to it. So this might be the asymptotic frequency. So that's the frequentist that lied to you. You say 95%, but it's really like 13%. And we have an example where that would happen, and I trust that all of my like conscientious frequentist friends would have said, I wouldn't have done that. I've got a better interval. So I'm sure that they would. I don't know why we teach this other way. Or at least use it as sometimes it works okay and sometimes it doesn't. I kind of like that. Makes you take another class. Figure out what it all depends on. But that's what a confidence set or interval is. It's an a priori process. So I might follow that process and give you this interval, and I'm not saying whether or not it covers or not. So I've got this one interval right in here. I'm going to say this one. So let's say this is the one that I actually observed. This is the one I computed. These are a thought exercise to tell me the frequency of coverage is supposed to be something, but at the end of the day, I've computed that one. And I say my procedure is such that 95% of my intervals cover the truth. And so what you said is, I'm a good statistician. 95% of the time, I give people good answers. And 5% of the time, I don't. And that error rate has to be inherent to the calculation. A lot of people are like, when things go wrong, they're like, what happened? That's what 5% means. Even though you are saying you're willing to make errors some of the time, and I think that that's honest, that's reasonable. Of course you don't know, the data was stochastic, so it's these boundaries that are jittering around. So that's what's random in all of this. You know, and so you're saying 95% of my clients I've given good answers to this year, and 5% got bad answers, and we don't really know who they are. So that's what it really is. And back in the day, if we were in the 1940s and people were talking about this, they wouldn't be super compelled. In my day, if you said the definition of the confidence interval wrong, -10, you know, that was like a big deal. And if you said, I think it's the probability of theta being inside of the interval, and you'd say, well, this is a weird way of thinking about probability, I guess. You know? They'd say, well, you haven't constructed, that doesn't follow Kolmogorov axioms. That's not what they talked about. -100. You know, get it right. And there was a big divide back in the day. But let me show you something in a particular problem. So let me just give you an example. So this is the normal example that I think we all learned first. So if I have SIs coming from a normal distribution with mean mu, variance sigma squared, I get n IIB realizations. And I got this big question mark about that, but I know this. So this is the example that most of us get taught in high school or in college and so on. And so how do you form this interval? The interval looks like this. And I'll just write this down. This is where it's coming from. This is just the probability x bar plus 1.96 times sigma over root n. And this is x bar minus 1.96 sigma over root n. And so you'll see statements written like this. This is almost true. You need a few more data points for this to be 0.95. You need a few more decimal points, but that's really close to being true. So it's not exactly 196, but we learned that number. I'm just going to rewrite this. This looks like this. X bar minus a certain mu, and I'm going to call this just a mu star, so I have something to think about when I plug this thing in right here. This is sigma over root n, and this is going to be less than some threshold. Is equal to 1.95 right here. This threshold is 1.96. So it's what we would come up with. This is normally distributed. The reason why is because X bar is the thing that's random. So X bar is random. I'm shifting this. If this is the truth, it's going to be centered at 0. So you'd use this form if you were hypothesis testing. And we'll see this later on in the class. But this sort of standard stuff, and this makes it a standard problem. I'm just standardizing the equation. That's called a z-score. So this is typically called z, and the z is random. And I can untangle this and write it like this. This is the same thing. What's random here? It's these. This is what's random. So if you think about this randomly, that's what's wiggling around all these bounds over here for different data sets. So if I come up with different X realizations for every set of data, I can compute another confidence interval, and that thing's wiggling around. And people have long, arduous conversations about what is probability, how am I allowed to think about this, and it's restrictive. So, but this is a statement about the process. And if you're interested in controlling error rates and things like that, you would want to understand the process and frame it in that language. And I think that there's cases where that's totally appropriate. Here's what a Bayesian would do. So Bayesians don't adhere to needing to cover. That's obviously a contentious conversation. If you had an opportunity to cover and you're living in a frequentist regime, if I did a Bayesian analysis and I weren't covering okay, I would think there was a problem. So I sometimes adopt Bayesianity to become a better frequentist, and we've seen cases where that happens.
I'm just curious about the notation for the confidence interval. So on the board, it looks like it's saying that the probability that mu is between the lower bound and the upper bound is equal to 0.5, but that's not what it actually means.
It means that this endpoint right here, these endpoints right here, we're able to cover the truth.
Yeah,
So it's a probability statement about the endpoints subsuming the truth. So what does that mean? The endpoints, wait a minute, I just have one data set. What does it mean about my one data set? You are in the same predicament as everybody else. So if you're confused, genuinely confused by that, thank you. Glad. That makes me happy. So, because it's this fictitious thing, go back, it's a statement about the process. So the probability statement you're making is not an inferential statement about your data, it's a statement about your process. So this is the next part where you're like, what is the probability of theta being inside the interval? And they say, well, it's 1 or 0, it either happened or it didn't. So, well, thanks, you know? Let me give you a different way to think about it. So when your smart aleck teacher tells you that, you can be even more smart aleck with them. And I wish somebody told me this, and people always ask that question, if you could go back in time, it's for this one thing, I want to do this. So, if I were a Bayesian, Bayesians make intervals and sets as well. So, Bayesian intervals go by the nickname of credible sets or intervals. I'll give you an example with sets in a moment. Pick up with it next time, and then we're running out of time. But if I were a Bayesian looking at the exact same problem, what I would do first is I would construct my posterior distribution. X sigma squared. And this thing is just going to be a normal centered at x bar with variance sigma squared over it. I have an assumption built into that. I use the flat pi. So pi mu is flat. So I like to write it like that, but if you like to multiply by other numbers, you're allowed. So don't make them too big or too small on your computer. It will possibly be. I come up with that right there. I can think about this distribution. This is x bar, it's centered there, has some scale. I usually take the square root over that and I describe it so that it shows the distance to the inflection point. And then I just think about this as my belief about where mu is. And so Bayesians have a lot more flexibility. What is probability to them? It's a measuring stick to tell me where I believe mu is. So I've built a clever measuring stick. That's all it is. If you want to make it sound fancier, take a measure theory class, and they'll give you lots of fancy words for this measuring stick, but it's a coherent measure. It follows all the rules of probability. And it tells me where I believe mu is, right here. So if I wanted to pick the densest interval or a symmetric interval, right here, that's 95%, I'd chop off my 2.5% tails. This is going to be 0.025 area, and this is also going to be 0.025 area. And I could look at these 2 points, and I can describe that. And what I would get for this left-hand point is this would be x bar minus 1.96 sigma over root n. And this rightmost point would be x bar plus 1.96 sigma over root n. You get the exact same answer. And the Bayesian said, this is my belief about where mu is. And I'm not making a statement about the process. X is fixed on, so conditional on my one data set. This is where I truly believe mu is. And there's lots of good mathematical properties for taking that as a measure. And we've seen a few of them. So we at least saw that it appealed to some rationale. If we were willing to think about it as a classicist as well, we also say this has great coverage properties. It's not asymptotic. This is exact because the original xi's were normal. So, and that's the way it would come out. So there's complete agreement in this example, but there's not always this agreement. And this agreement happens because of the symmetry between mu and x bar in our example. So it's not always going to happen. So what I would like to go back to say to my teacher about, well, I'm not allowed to think that this is where mu belongs. So I could say, well, I'm also Bayesian. And I used a flat prior, and I came up with the same answer, and I get both answers. And that is nothing to fight about. That's actually really great. We all come up with the same interval. A lot of stuff is asymptotically normal, so whether you're a Bayesian or not a Bayesian, I would agree, just as long as you use this. But if you want to say, not so fast, don't slap my wrist. I'm a Bayesian, and that's the way that I like to think about it. So that's probably what David was thinking about, is he was natural born, Bayesian, and it's a belief statement about you. And you can have them. I want to look at this example. This is just going to take me 30 seconds to write down. We're going to glance at this, and it's going to set up an interesting predicament. The Bayesian's going to come up with a kind of very different answer than the answer I'm going to coach you into, and I'm just going to say, hey, this covers, so we're going to need other frequentist properties if we want to talk about coverage alone. But I want to consider this problem. Xi is going to be Bernoulli. So this is either going to be a 1 or a 0 right here, and I'm going to have a parameter in here. And I'm going to say this is theta plus 1. So I'm going to make this kind of weird. So this is some sort of a, actually, I'm going to do this. Let me do this. This is the way the problem goes. This is easier to do, and I don't need all kinds of weird constraints. Theta plus 1 is Bernoulli, right here. So this could either This is just some realization right here, and I kind of made this either theta plus 1, and there's this other possibility, theta minus 1. So I'm going to say the xi's, let me write it this way, xi, where the xi's can be either theta plus 1 or theta minus 1. This is the right way to say this. And I'm going to say this happens with probability p. This happens with probability p. Obviously, if I don't sample a heck of a lot of times out of this, I can't learn these two things. So I'm going to make this problem even simpler. We'll talk about, this is 1 minus p right here. So I'm going to make it real simple up front, and we'll talk about changing this later on. And we're going to try to build an interval or a set for trying to learn what thetas are. So you don't get to know up front what this shift is. So these realizations, you're not sure where they're centered around. So this is a location parameter. And that's kind of a heads up for when we do a Bayesian analysis of how would I cut a prior on this? So what would I do with that then? So Bayesian can cut a prior on anything they don't know in the model. And just operate through the likelihoods. So the big trick to getting this problem right is writing down the likelihood correctly. So I'm going to ask somebody to be courageous and come to the board and do it next time. So you can see if that's you. So the likelihood. So let's make the problem really easy. And I'll say I goes from 1 to 2, so you only get 2 realizations. We'll make this problem a little bit hard. If I got a whole bunch of samples out of this, I would know what the theta was. I'd know what it was real quickly. So if I ended up seeing these 2 things and I saw different realizations, I would know what theta was instantly. So this problem. But if I got 2 draws that were the same, there would be some uncertainty, and the way we express that uncertainty as a Bayesian or a non-Bayesian might be totally different. So that's where we'll pick up. There's a paper on the website that addresses this, and it's called Could Jeffries, Fisher, and Heyman Have Agreed? That's the name of the paper. So you can look at that as well. That's all ready to go for you. If you want the one-word answer to that paper, the answer is just no. Not on anything, no matter what.